Why this course, Design of Tall Buildings and Bridges? Why do we want to learn about this particular course? And what does it cover? Let's talk about that first. Tell me one thing, what is this? Which city is this? Dubai. How many people do not know it's Dubai? Everyone knows, right? Why? Because of Burj Khalifa, because of the tall buildings. The city is identified by tall building, Burj Khalifa. So everyone who sees this building, they immediately know it's Dubai. So which means the symbol of Dubai has become this building. So the building is so important that it defines a city or a country completely. And by looking at this building, everyone knows it's Dubai. Everyone. No matter whether it's engineer, non-engineer, whoever it is, they would know it's Dubai. So tall building, which means is so important that the cities or the countries, they use it to show this progress in their country. They want to, if they want to promote tourism, they want to promote their country, they want to promote their city, what do? They build a tall building, right? That's only one purpose. There are other purposes, but this is one purpose, that this tall buildings, actually really tall building, and you can see how tall it is compared to other buildings. So a really tall building defines the progress of the city or becomes a symbol and an icon. What's that? Where? See? A bridge. You look at the bridge, picture of a bridge, and you know it's San Francisco, it's Golden Gate Bridge. Every movie, X-Men or whatever, they destroy the bridge or they take the bridge away. Everybody is trying to destroy the Golden Gate Bridge, right? Or they show the Golden Gate Bridge. It's so important and so iconic. So which means basically two things, tall buildings and bridges. They define cities. They define cultures. They define the whole symbol of development, progress. So, which means that what we are talking about, this subject or this topic, we are covering these two very important infrastructure elements, tall buildings and bridges. Of course, not all of us will get a chance to design Burj Khalifa or get a chance to design Golden Gate, but the principles are the same. I can assure you that the principles of designing Burj Khalifa or what we are going to study here are not much different. We are going to learn or we are going to study the principles or the background or the tools that they use in Burj Khalifa. This time, this era where you are born and you are working is an era of equal opportunity. So structural engineering, main achievements in tall buildings and bridges. So if you ask a structural engineer, I don't know about you, we used to dream, oh, let me design the tall, some big bridge, some tall building. That's how we define structural engineering, right? Structural engineering is an art. So structural engineering is, in art, or the two sentences that you should think about. Structural engineering in art and art of structural engineering. One is that the use of structural engineering in assisting people who are creating art. That art could be a bridge project, could be an architectural monument, it could be anything. If somebody has conceived something, an architect or anybody, and you help that person to create that, to make it real, that is structural engineering. Architect cannot, they dream. You make it possible. Structural engineers make it possible for their dream to come true. They dream about donut-shaped building. They dream about all these funny things in Dubai. Who makes it possible? Structural engineers. Twisting buildings. So architects think about twisting buildings. Who makes it possible? Rotating towers. Bridge between connecting two islands. Some transportation people dream about connecting two islands. Structural engineers make it possible. So the people who dream are the artists or dreamers, and structural engineering helps them to achieve their dreams. That is structural engineering in art. Second one is art of structural engineering itself. That means, any discipline, any field has levels. First of all, everything starts at philosophy. Philosophy, in the old times, we didn't have physics, we didn't have engineers, we didn't have anybody. We just have philosophers, the guys who have all the knowledge. Like Socrates, Plato, all these guys. They are good in physics, they are good in everything. The whole knowledge of that time, one person could possess. They were philosophers. Then after that, mathematicians become scientists separate. And then mathematics and science separated to physics and chemistry. And engineering can come from physics, and physics and math combined in engineering. So it went on going into specifics. But ultimately, the top of everything is art. Artist is a person who doesn't need to follow the rules, but still create something. So engineers who can create something without calculations, without doing anything, they just understand it. They're so good at it that it just comes naturally to them. They become artists, structural artists. And there are many people who have been through that without computers, before finite element analysis, before everything. They created all these marvels without any calculations, because they just understand how things work. They just can create something. And those are, so the ultimate level of anything, any discipline is that it becomes an art. Not a process, not a commodity, but an art. So structural engineering, the art of structural engineering is taking the structural design to the level of an art. That you have become an artist, that you are top, you're beyond science, you're beyond calculations, you're beyond everything. You just dream and you create and you make it. And that's it. That is the artist, structural engineering artists, right? So that is the ultimate level that few people can reach that or have reached that. These days it's a little bit more difficult to be an artist because so many rules, so many codes, so many something. But in the past, it was quite possible because there is no other way. Let's talk about this course now. So this course is going to be divided into these two groups because we are dealing with two subjects. So I have tried to integrate the two subjects so that we can continue from one course to one subject to the other. We will start today, as I'm starting today, Introduction to Structural Engineering Design and Approaches, one lecture. Second topic will be Introduction to Tall Buildings, one lecture. Then we will move to Introduction to Bridges. I thought a lot about it, that maybe we should finish the buildings first and do the bridges later, but I think that's not a good way to go. Reason is, I want to give you option to choose your project, term project, tall building or bridge. But if I teach the bridge later, then you will not have any knowledge to do your project, those who want to do the bridge. Okay, so this is where we will go. We will do that one. Then there's going to be a common 2 lectures on finite element modeling and analysis, which is common to both the courses. And actually, I'm hoping that Dr. Panchit will also be offering finite element, but he will be offering theory. I will be offering practice. So this is a little bit before time. Then building structural systems, then bridge systems. Modeling analysis of gravity loads for buildings, modeling analysis of superstructure for bridges, modeling analysis for lateral loads, modeling analysis of substructure, design of building components, design of bridge components. So they will go hand in hand. One course, one lecture on buildings, one on buildings. So you can also compare how the two are similar or different. Okay. And finally, after this is midterm here. So after this one will be midterm, and then we will start the project. One real building, 40-story building, you will be required to design completely in groups, and one real bridge that you will be required to design as a group. All right? So that is the plan for this course. These days, the buildings and structures are expected to be, we should remember that the public expectation of the structure is changing. Forget about Golden Gate Bridge, forget about Burj Khalifa. There are millions of smaller buildings being made. There are thousands upon thousands of bridges being made, which are more useful or used by the people on daily daily basis, and you will be working mostly on those. So all of those need to be safe, they need to be secure, they need to be serviceable, reliable, protective, friendly, sustainable, and affordable. All of this is the expectation of the public. Non-engineered people, they want their buildings to be like that. The contents of the structures are often more valuable than the structure itself. Do not forget that. Most of the time we think structure cost is very important. Actually, structure cost these days is much smaller than what is inside the structure. Like a computer center, like a hotel, like a hospital, the cost of the equipment and the furnishing and the things inside is much more than the cost of the building. So a damage to the structure is not that important to the owner than the damage to the property inside. So it's not only that we have to protect the structures, we also have to protect what is inside the structures. It's not enough to say now, these days, that my structure is going to be standing after an earthquake or a windstorm. No. It is also important that nothing in the structure will also be damaged. So we have to consider both structural and non-structural, and also important thing about sustainability. Everybody is talking about environment, climate change, and the sustainable structures. So you cannot just make a structure without considering environment and sustainability. So the game is changing. It's no longer designing reinforcement and think, I've done my job. Not enough. You need to think beyond that. You need to sit in a meeting where people will come and say, have you considered sustainability? And you're looking at him, what? Because engineers do not know what sustainability means and how it can be included in their structural design. Those things are important. So, loss of service operation business is often larger than the repair cost. When you shut down a building for repair, the cost of this repair may be small, but the loss of the profit from the business or the operation that was going on in the business is too high. If it is stock exchange, imagine, stock exchange of Thailand, building is damaged, they have to shut down or move. The cost is too high. One day may be more than the whole cost of the repair. So the structure, services, and inside what is structured needs to be protected too when you design. This time I have two students doing thesis on non-structural component, damage to non-structural components due to earthquakes. Looking at what is the cost of that, because we need to be able to design for that. Structural engineering is a big field, very large spectrum. It is very broad. If you look at it, in terms of the engineer, they are required to do many things. Conception, analysis, design, detailing, and so many things. There are many structures to design, buildings, bridges, trusses, shells, towers, and so many others. There are many codes to follow, American, British, European, and so on. Many materials in which you can design, concrete, pre-stressed concrete, steel, timber, composite, many modeling that you can do, many analysis that you can do, linear, non-linear, static, dynamic, many types of solutions you can follow. So it's a very broad field, too many things to do. And no one person can be an expert in all of that. Or maybe you can by the time you reach my age, but not so soon, right? But, so you have to choose a little bit about what is the specialty that you want to go and work in terms of the type of structure that you want to specialize, in terms of the materials that you will be focusing on, and so on. If you're going to work in international organizations, building codes, you have to learn many. One may not be enough. That's why last course we tried to learn things beyond the building code, right? So that you can use any building code. Linear analysis, you should be able to do different types of analysis. Simple analysis that people do, not enough anymore. You have to go beyond that, especially if you have done master's degree. People will expect you to go beyond the normal. So we need to learn all of that. Design office, as I mentioned, in a typical design office, engineers are required to do these activities. Conceive, conception, create the concept, develop the building system, develop the structural system, think about how to solve the problem, the bigger decisions. Analysis, modeling and analysis, then design, then detailing, then costing. So you need to know the costing. Many of my theses this time are related to costing. For example, finding the least cost bridge type for a flyover. What is the most economical span for a bridge? What is the most economical structural system for a building? So cost becomes important. So if you have no idea about costing, you cannot be a good structural engineer, because that's the first question anybody will ask you. They will come to your office and say, which is the most economical structural system for my building? What do you say? Let me work on it and I'll tell you after 1 month? No, they will say, okay, bye-bye. Let me go and find a person who has the answer right now. So you need to have this knowledge and understanding of the cost related to structure and the structural systems. So all of these things and detailing, no matter what you do, final output of your design is detailing, the drawings that you send to the site. The person who is going to construct the bridge or the building, they only look at your drawings. They do not care, or they do not know which software we use to design, what method you use, nonlinear analysis, linear analysis, which code you use. It doesn't matter. All they have is a drawing in front of them telling them, make a column of 1 meter by 1.2 meter and put 24 bars, 5 here, 6 here, put the ties here, the spacing of that. That's it. Put a concrete of this strength. That's all the information they have and they want to know. How that information becomes a real structure is up to you. So detailing is very important. All right, so we are going to talk about this. So in our class, in this one, we will be looking at all of these steps. Most of them for buildings and for bridges. Now this is the typical way that most engineers should work. They should start with conception. Conception means idea, how to solve a problem, how to design a structure, what system to use. Then go from that to modeling, convert that idea into a model, into a mathematical model or a computer model. And then from that modeling, go to analysis, analyze the structure, analyze that model, not the structure, the model. Then design the elements, and then do the detailing, and then drafting and costing. So that is how, step by step, we go from one to the other. Yes, you want to ask something? You. No? Just waving your hands. But most of the time, this is not possible. This, theoretically, it should go like this, step by step by step. But actually, it's not possible. Because I mentioned to you, the client may come to you and say, tell me the cost of this system, bypassing all of the other steps, which means that you need to know the answers to many things without going through the process, which is very difficult, very strange, because you haven't done the design yet and somebody is already asking you the cost. And you might say, this is ridiculous, but that's reality. And then when you start something, when you start with the process and you finish everything, the client change their mind. They say, oh, no, I don't like this. Can you change this? Then you have to go back and revise. All the time things are changing, so you have to keep on going up and down in your process. That's why we say that this is an integrated design process. That means all the steps are happening at the same time in your mind. So a good structural engineer, a good engineer should be able to do everything at the same time. So when he or she is doing the conception, the cost is already in the mind. Doing the modeling, the results are already in the mind. So you develop this sense of the whole process in an integrated manner. So once you have enough experience, enough knowledge, you should be able to do that. So you can divide the process into three main categories. Whether it is bridge or building or any design, it is three groups of activities. And I'm going to talk about each of those groups in different lectures. First one is conceptual design. Most important step, conceptual design. That means what is going to be my solution to the problem. I have a problem. The architect is saying that I want to design a building, 50-story, 40-story, that is my planning. What system am I going to use? Concept of the system, structural system concept. So this is called conceptual design. So first lecture, 1 or 2 is going to be about this part, very important part, because if you make a mistake here, you will go in the wrong direction. It's just like you want to go there, but you start in this direction. You have to do a lot of corrections to go to that direction. So the structural system must be more or less in the same direction that you want to go. So that decision is very important. Modeling and analysis, this is technical, highly technical steps. This step requires thinking, imagination, innovation. This is more or less mechanical. Mechanical means more or less procedure, more or less learning the techniques, the tools, how to do things, learning the program. So trial sections, modeling, analysis, this is combined together into one process in which you need to use the software. So this is more about using the software and trying to use the... So we will spend 2 lectures on this part, 2 plus 2, 4 lectures on this part. This one is called design and detailing. That means after the analysis is done, you get the result, then you have to figure out what size of member you want to use, how much reinforcement you want to put, then your knowledge of... So in this case, we are going to talk about the concept. Here, you will need the knowledge from Dr. Penning, Professor Penning, about dynamics, from Dr. Panchit, about structural analysis, about finite element analysis. Those kind of backgrounds will be needed on structural analysis, theory of structures, structural dynamics, wind engineering, earthquake engineering. All of those will come, moving load, those kind of things will come here. In this group, design and detailing, we are going to talk about design of components, design of beams, design of slab, design of foundation. So you will need knowledge from concrete design. We are not going to do steel, so steel can be out. We are only doing concrete. So you will need the concrete design knowledge. You will also need some knowledge about foundation design, things like that. And then we will get the detailing. We will talk about it a little bit, and then final output. So this is the overall process, and this is how this course will go. So when you start any design, I'm talking now about the first part of the group, concept design. You need to really understand. See, please remember, this course is very practical. So we are talking about the actual way things work out there when you graduate. So when you start a project, you need to go through what is called a pre-design phase. Before you design, you have some information gathering. You need to gather information, you need to collect data, you need to understand the problem. So this is called a pre-design phase, in which you talk to people, talk to the client, talk to what do you want? So it's more like understanding the problem before you start designing. And you talk to many people at that time, or many people will come and talk to you. Then site analysis. Second part is where it is going to be made, this structure, bridge or building. Is it going to be in Thailand, in Philippines, in Myanmar, where? Because that will govern many things. It will govern the loads, it will govern the codes, it will govern the material, it will govern the construction methods, it will govern many things. So you need to understand where is it going to be. Not everywhere is the same rules apply. So location or the site is important. Then also about the location, what is the ground condition, what is the seismic loading, what is the wind direction, all of that information will be needed. So first one, understand what is to be built. Second one, understand location and site where it will be built. And then we do a preliminary design. Preliminary design means that we do some simple hand calculations or thumb rules, or use our knowledge and experience to come up with some solutions, possible solutions, right? And then we go to the detailed design. So that's how the process works. And this is for any project, doesn't matter. Building, bridge, water tank, anything that you want to do goes through the same process. Now, what is the main, coming back to our role as structural engineers, what is the main purpose of design? So if you look at the very main purpose of the design, there are many purposes. Very main purpose is this one. I showed this slide before also, right? No? Yes? Never mind, you forgot. So don't worry, they forget already. You guys, they forget already. This one is structural design is the process. Please understand this definition very clearly. It contains very deep, important meaning. Every word is very important. So structural design is the process of proportioning the structure to safely resist the applied forces in the most cost-effective and friendly manner. So it is a process in which we have to proportion the structure. What does it mean, proportion? Proportion means sizing, members, materials, reinforcement, how they are put together. Everything about assembling the structure or defining the structure is called proportioning. And that is the main task, to proportion the structure to serve its purpose in such a way that it is safely resist the applied forces due to any reason. At the same time, it is cost effective. That means the cost is acceptable within the range, within the acceptable range. You cannot just make something that is so expensive that it cannot be made. Unless it's Dubai, they just make anything. But in other real world, other than Dubai, cost is very important. And friendly manner. What does it mean, friendly? Friendly means everything friendly. User friendly, environment friendly, sustainable. Many friendly things come into. So it's not only safety, but all the other things come into play. So structural design is a process in which you take a requirement, you form a system, you find the sizes in such a way that it is safe, number one. At the same time, cost is acceptable, number two, and it's friendly, number three. So all these three things are very important, and these are big definitions. Okay. So in theory, load, requirement, constraints, go to the design and come up with the outcome which can be sent to the site. Material specification, cross-section design, member sizes, configuration. So this is drawings. So basically it's like a black box to outside world. They hire the engineer, they give them the requirement, and they expect the drawings to come from this side, right? So it's just like, it's like a machine. You put something in there, and outside you get the drawings out. But inside, there are many things to do in this design process, and that's what we are trying to learn. Let me just talk about the two important definitions, structural analysis and structural design. You will hear this term a lot. Analysis and design, structural analysis and structural design. Both of them are part of the design process, but they are very, very different activities. And sometimes in big organizations, engineers who do analysis are a different group, and engineers who do design are a different group, engineers who do detailing are a different group, engineers who do costing are a different group, engineers who do conception are a different group. So if you're working in an organization like Arab or some big organization, you will be in a department which will only be doing one part of the job. But if you're in a small firm, you will have to do everything. So analysis and design. So structural analysis is a procedure in which basically you take the structure, you create a model of the structure, you use a computer program, and you calculate the response of the structure. and then you stop. Design is a process in which you take the response of the structure and you use that response to find the sizes and material specifications and reinforcement and section sizes and after that send it to the drafting people. So analysis is general, can be applied using the same software for everything. Design is very special. Different design procedure for beams and columns and steel and concrete and slabs and so on. So design is very broad. Analysis is more or less can be standardized, can be generalized. So we will spend time on this as well as on this. Let me skip this one today. The one question that you will be asked in your career when you work in the field or in anywhere, is my structure safe? People will come to you, clients, public, your family. I live in a building and I was going in the elevator and we just started talking and the guy said, what do you do? I said, I'm a structural engineer, structural designer or something like that. He said, is this building safe for earthquake? And we just met. And the first conversation he has with me is he's asking me, is this building where we are living? And he expects me to answer that question without doing anything. And he expects me to know right away that this building where I'm living is safe for earthquake or not. That's his question to me. What can I answer him? Let me make the model, let me go back to the office, give me 100,000 baht or whatever, and then give me 6 months and I'll come back and give you the answer. He will lose interest at all, completely. But this is the most common question you will be asked. And unfortunately, structural engineers do not have the answer to this basic question. I just told you that the main objective of structural design is safety. But after that, we still cannot answer this question. Actually, you cannot say that it's safe. Because safety has a very difficult definition. Also, what you have done is, we'll go there in a minute. But if you think you can answer that question, you are wrong. Stop thinking that you can answer that question. Should we be able to answer this question? Yes. People expect that. You know, when you buy a cell phone or anything and it doesn't work, you have a warranty. You go to the shop and say, it's broke, it didn't work, give me the new one. But if you're designing a structure and it doesn't work, and if the client comes to me, give me a new structure now, it didn't work. Can you give him a new structure? You cannot. We cannot warranty our structure yet. This is a big problem that we will talk about. Anyway, so this is the question that we want to answer. And if somebody asks me this question, or somebody asks a question, an engineer will ask back, what do you mean, safe for what? Earthquake? What earthquake level? How many Richters? Or the client may ask, is this safe for a tornado? Is this safe for an earthquake, level of Richter 9? Then they will also ask you a question, what is the life of the structure? Simple question from the public point of view, and structural engineers do not have the answers. What is the life of a structure? Do you know? Can you answer that question? And the next question is, what if I want to increase the life of a structure? What will you do? Can you design a structure which will last 200 years? Or 100 years? We don't think about this, because we don't relate the structural design to the final questions that the people are asking. So that is why the structural design process is going through evolution, changing of the design philosophy, design approach. And I want to tell you where we are going. We will not go there in this class, we cannot. But at least you know where we are heading as a profession. This is what is happening in structural understanding over the history. Long time ago, we started with certain methods and now we are going and changing and evolving into newer methods. And I want to share with you how this process is going on and where are we at this time and where we plan to go. Not you and I, but engineers in general. So this is the steps that we have to climb, that we are going ahead now. First step was intuitive design, which was history. People before computers, before calculations, before mathematics was invented too strongly, pyramids were made. 7 wonders in the world, most of them were made before computers, almost all of them, which means that people had some understanding of designing huge things without calculations. That was intuitive design. People just knew something through experience or something. They could create this enormous, huge structure or wonders. So that was intuitive design. It still works. You can still do that. So what you can do now is that you can do the intuitive design first, and then you can check the design by other methods later. The best way to learn structural engineering is to do the design without calculations first and keep it on the side and then say, okay, let me check what I did. Rather than start the process like I shouldn't use the word, like as if you're trained to do some work, So robot, or don't do that. So the good way is that when you get a problem, you say, I will touch the computer later. Let me think what the solution might be. Let me think what the column size should be. Let me think what the reinforcement might be. Just think from your side. Don't do any calculations. Imagine that you are living 1,000 years ago. What would you do? If you were living 1,000 years ago, how would you solve this problem? Where you had no calculators, no computers, no nothing. Only you have your brain. How would you solve that problem and solve it? Keep it on the side, then go to the next steps, then cross-check. Then you will learn much faster. Anyway, so this one was the old time, or it can still be used. Intuitive design, only from your mind, from your intuition, you can design. But then came codes. Code said, this is not good enough because because you are dealing with public safety. You cannot play with public safety. What if your intuition is wrong? People will die, right? So building codes came in, regulations, rules. They said, no. You cannot do your intuition too much. You are not as good as people in the past. Because why? Because in the past, only the masters, a few people in the world could build buildings of that kind. Now we have millions of engineers. So not everybody is of that level. So building codes come and define what you can do and what you cannot do to protect public safety. So that a large number of engineers can now do the design following the building code without doing intuitive. The ones who do not have the capability to do intuitive design can follow the code. And this is problem number 1, why we cannot answer that question, building codes. And you know me, I have been always against following the building codes blindly, right? So another time, building codes is one reason which prevents innovation. But they have a reason to do that because they don't want people to go out of control for public safety. So building codes is the second step, which is where we were or we still are in this time. So we must follow the building codes, otherwise your design will not be approved, will not be built, people will not believe you. So following the building code is now a requirement to some extent. So if you look at the building codes, the first building code was written in 1666. There was a great fire in London. The whole of London burned down, if you study history. And after that, they said, no. We must have fire code. We must have building code to make the buildings fire resistant. We don't want London to burn down again. So the first building code was developed basically to make the buildings fireproof, to make sure that the buildings will not catch fire, or they had at least 2-hour fire resistance rating so people can get out. So that was the first. After that, 1680, the laws of the Indies in Spanish crown in Spain, they made laws for buildings. So it started that time ago. Then London Building Act 1844, and then in USA the first building code was introduced in 1859 in Baltimore, and then after that 1904 building Baltimore City Code, and then after that 908 first building code, and so on. And after that millions of codes came up. Now we have thousands upon thousands of codes. But only in the last century, from here, after we have the International Building Code IBC formed, and then European codes came in and British codes came in. So that is the history of the building codes. So it started with that, and now we have so many building codes in every country, in every region, every city. We have lots of building codes, very, very complicated. That many, some books, some codes are very, very thick. And most engineers have never read them because they're so busy doing the work that they only read parts of the code, they don't understand the whole code. But anyway, so these are the building codes. And we must learn parts of the building code in any case. Please try to understand the building codes, what they are used for and what is their objective. Basically, the objective of the building code is to make sure that we design something which is safe for the public. Minimum standards are followed. So we don't do something which will lead to unsafe structures or to a situation where public safety will be affected. So they give you all these rules, extremely detailed prescriptions and equations using numbers. Do this, do this, do this, do this, do this. I don't want to go into detail, but basically they give you all these. This is some requirement from the code. This is from American code. This is from IS code. And they give you these numbers. Very clear limits. This. So they try to define everything for you. But these definitions are not real. They are basically intended to give some control. Okay, we'll come back to this one. The problem with the building codes is that they cannot cover every case in reality. So they try to cover some normal common cases. So if you want to do something beyond that, building codes may not help you. So you have so many building codes from various countries. The question is always, I ask this question, are all building codes correct? Suppose you are sitting here in Thailand or in your country and you design a building according to British code, American code, Thai code, Russian code. Will you get the same answer? What do you think? Yes or no? No, you will not. Then the question comes, which answer is the right one? If you get 6 different answers for a beam reinforcement, which is the correct one? What do you think? 7 answers cannot be right. Correct? So the question is, which one is right? If none of them is right, then all of them are not right by logic, right? So that is the problem, that there is no right answer from the code because the codes, they are different. Second problem is that they keep changing every 3 years. So what they said 3 years ago as right is no longer right today. So after 3 years, it will not be right again. So whatever they're saying now is by definition wrong because it will change after 3 years again. The load factors keep changing, everything keeps changing every 3-4 years. So whatever the codes are saying now actually will change tomorrow. So should we go back and change the buildings that we designed in the last code? So what happened to those buildings that we thought were safe last year, no longer safe this year? So are the buildings safe or not safe? Safe last year, not safe this year. What kind of answer is that? Safe according to BS code, not safe according to ACI code. What kind of answer is that? So if the earthquake comes, can we tell the building, this is 1977, please follow code 1997 UBC, right? Because we designed for that. Cannot. So reality and codes are not matching. That's the problem with the codes. But we still have to follow the codes because that's the minimum requirement. But they do not give you the confidence that you are saying that after I design the building, I can say the building is safe because you followed a code. So how can you say the building is safe? You can only say that I followed the code. That's all you can say. And that is the problem with structural engineers, that we cannot. So this is what I just said. But the codes intend for life safety, not damage. That's another big problem. The main intention of the code is safety, not damage. So they don't care if a computer inside a building is damaged or not. They care that the life should not be lost. But the client cares about the computer as well. The computer inside a building or whatever they are put the equipment also should not be damaged. The windows are very expensive, should not be damaged. Right? The ceiling is very, they've imported the floor or something from, and it's very expensive. So they don't want it to be damaged. But the codes cannot guarantee that. The codes do not care about that. Codes only care about public safety. So the clients are saying that by following the codes, you are not giving me what I want. I want a building which is not only safe, but it is also going to protect my equipment and things. And it will, if there's a damage, can be repaired. So there are many questions that the codes cannot answer, which make us to go to the next step. So this guy is hiding behind the codes, structural engineer, saying, I don't know anything, I just follow the code. Right? Don't ask me, ask this code. And that's exactly what engineers say. Whenever something goes wrong, they go to the engineer and they say, no, I followed the code, you can check my calculation. But if your calculation is okay and then the structure fell down, why? Of course, there could be other reasons. But the question remains that we need to do better. And that's why we have that ladder where we have to go. Let me skip that and give you something interesting. This is a reading from Hammurabi. Hammurabi was a very, it was like a king long time ago, and he made all these laws of Hammurabi. If you read them, very threatening, very dangerous, because one of his laws, and he did a lot of work, and it was long time ago. It was before, so 2,000 years plus 1,000, so it's about 4,000 years old law, 4,000 years old. And it was written like this on tablets, no paper at that time. And it says, if a builder builds a house for someone and does not construct it properly, and the house which he built falls in and kills its owner, that builder should be put to death. Eye for an eye. So if you, structural engineers or builder, at that time no structural engineers, builders, did not build the house, design the house properly, and somebody died, you must die also. That is the rule of the law. So that was the first code, building code, regulation. But they did not tell you how to do this. They did not tell you put so much reinforcement, put this one, they just make the law. Do it well. Whatever you do, do it well, so it does not fall down. So responsibility lies entirely on the builder, 100%. So the builder must use whatever they want, they can. This is the intent of the new thinking, that we should do whatever we can to make it safe, not follow the rule and say, I follow the code. So this is 2,000, 4,000 years ago, some people start thinking about it. So there is a rule, there is a consequence, right? So it's consequence based. This idea is coming back now. Of course, not to kill the structural engineer, but to do. So now we are going to the next step, which is performance based design. So this code-based design is okay, but not the ultimate, because it does not satisfy what people want and what public want. So we have the next step in the ladder, performance-based design. This says we will satisfy some performance. So very clear performance objective, and you do the detailed design, you satisfy that. We do, so one of the things that AIT is now famous for is PBD, performance-based design. We are one of the few organizations or people who do this properly, and for the tall buildings especially. So PBD, or performance-based design, is a specialty in AIT. Not many people do this well. After that, so I don't want to go into detail so much, we have done so much work on that. So performance-based design is a new code, new way of doing things. Basically, you talk about not only the life safety, you talk about different levels of damage to the building. For example, this is operational, lights are on, everything is fine. This one is immediate occupancy. After windstorm, earthquake, temporarily you go out, after that you can come back. This one is life safety. This is what the codes are trying to say, that life should be safe. But they don't say what happened to the walls and the windows and the doors. So life safety is important. And then collapse prevention. So the performance-based design looks at each aspect individually in detail. So explicitly, after PBD, you can say that, yes, my structure is safe for a certain condition, right? So by code-based, you cannot. But performance-based design, you can claim that after doing that. So performance-based design is the next step. So you can relate performance-based design to the loading, to calculation, to everything. This is something that I will go into a little bit more detail. Maybe we will have a special seminar. This is Nepal. Last 2005, I went there and I took this picture. And this is the problem. This building is one of the tall buildings in Nepal. And after the earthquake, this is how it looks like. Actually, it follows the code. This is following the code. This is not an unsafe structure. If you look at the design calculation, nothing wrong with it. The code it is supposed to be like this according to the code. Because the code says, in this earthquake level, the building should not fall down. It did not fall down. Nobody died in this building also. Yes, 1%, okay, 1%, sorry, 1%, maybe something, but...
It's due to the falling of the brick.
Falling of the brick, okay, good. Thank you. So 1% because of the non-structural falling of the bricks, right? So theoretically speaking, this building is code compliant. But all the people who live in this building have to move out. They lost their homes. Most of them worked abroad, sent their money to buy this apartment, am I right? And this is high-class building over there, and now they have no home to live, even though the building was designed according to the code. So the public is saying, what is this? The code-based design is not protecting us. Because the buildings may have to be torn down or repaired for, I don't know how many, it's still like this, right? It is after 2 years and 1.5 years of earthquake, people have just lost it. So this is the kind of problem that is not acceptable by the society anymore. They want something better to be done about buildings and structures than just follow the code. So this is not acceptable to the public, even though this is what the engineers would be saying. So engineer is, if you ask the engineer, he's okay, he is behind the code, he's protecting him, right? So we have to go to consequence base. One more step. What is the consequence of damage? What is affected? If the life of the people is affected, if their livelihood is affected, we must look at the consequence also, not only about the damage and the risk of those consequences. So we go to another step. And this is now where many people are working. So this is code-based. Some people are here, very few, and very few are now moving to this level. And in future, we are going to the next step, which is called the resilience-based design. So beyond PBD, this should not, if you follow the next step, this would not happen if the building was designed following the next step. So many questions that PBD cannot answer are going to the next level. So, so consequence-based engineering has a very different approach. You know, normally as structural engineers, we are taught about designing for a load, designing for wind, designing for earthquake, for a certain level. But we don't know for sure if a stronger earthquake will come or not. Like for example, you remember the Japan tsunami and the Fukushima nuclear reactor. You know about that, right? You all know. And one nuclear reactor leakage, it leaked because of the earthquake. And the consequence of that event are so great that the whole country's nuclear power plants are shut down, and it just went on for many years. So people are saying that forget about the level of earthquake, forget about anything. If something happens, if the consequences are very great, it should not happen. Simple. So prevent something from happening so that we don't need to deal with the consequences if the consequences are very large, very great, like the power plant failure. So we are looking at those kind of levels. So the trigger of the event is not important, the consequence is important. Why this happened is not important. It should not happen. That's it. So you don't try to find the cause, you just prevent it from happening. This is beyond, that's your next level of thinking. So, for example, explosion in a building, like this thing in 9/11. Aircraft, that was not a load case that anybody designed. But the building was not designed based on this concept of consequence-based engineering. If it was designed, this would not have happened. Because that scenario should not have happened, no matter what the cause is. So now people are saying that we should design things in such a way that failures should not happen if it is big enough. Local failures is okay, but big failures should not happen. Like the two examples I gave you. So risk-based design procedures have come up. I don't want to go into detail. These are all advanced topics. There are many new codes that are coming up. We will be using some of them. We will especially be using this one. This is a very important document, peer guidelines for tall buildings. This is a new approach for performance-based design. And these are all beyond codes, guidelines, not codes anymore. They are called guidelines. That means they just tell the engineers you can do this, but they're not forcing you to do this. Okay, resilience-based design is looking at not only the building or a bridge, but what the thing stands for. For example, Golden Gate Bridge. It is destroyed in every movie. But what would happen if it really is destroyed or is damaged? The cost of the bridge will be nothing compared to the cost that San Francisco will suffer because of the bridge collapse. The people who commute every day, the economic loss of that bridge will be 100 times more than the cost of the bridge. So that means it's not just the structure, it's what it serves must also be considered. That must be, so the structure, if the structure is very important, it's a link between two islands, then it has to be designed differently than a bridge which is just connecting, a small town or inside a small town. Or if there are 7 bridges and one of them is destroyed, is okay, other 6 are still there. But if there's only one bridge between two islands and that is destroyed, it's a different thing. So it's not that you design the bridge individually, you think about what the bridge means to the community, what purpose it is serving. So you start to go beyond engineering, you go to the community level, you go to the national level. How will it affect the GDP or something like that? So you start to really think big in terms of, especially big structures like that. So that is called resilience-based design, that you have to look at many bigger things So resilience looks at quality of life, loss of community and culture, economic loss. Look at that. Structural engineers thinking about quality of life, thinking about community and culture. Did you ever think that as structural engineers you have to worry about that? Yes, in future you have to. Otherwise people will not respect you. Because that is the kind of talk that they use now in a meeting. The public expects you to talk like that. Not say, I'm designing a beam of 20 centimeter or 40 centimeter and I'm putting 4 bars in there, that's my job. That is ultimately going to affect all of that. So we must think on the big picture of engineers, what they're doing. So we link that to damage or loss, to casualties, to downtime for rehab, to rehab cost, retrofit, everything. So you think about everything when you design something. And you think about all of that. If nothing happens, it's great. But what if something happens? And something does happen all the time around us. We have seen it. So all of that impact on sustainability of community. How will it affect the community or country or a city as a whole? Because what you're designing is a big thing. That's why now we have this interesting thing. How many people know about LEEDs? Left side. Just one guy? Please, people. 2 guys. LEEDs. LEEDs is a certification for green building. Do you know about green buildings? What is a green building? Color green? Painted green? What's a green building? Environmental, climate change, everything, big picture. That if you want to make a building good, you make it green. That means it's environmentally friendly, it uses least energy, least resources, it's sustainable, and everything up to that. And LEEDs is one of the certification. So if you want to make the best building, you get a certified LEED building. LEED Platinum building is the highest certified building. LEED Gold building. So you have to follow many requirements so your building can be rated as green in different categories. What about safety? So engineers are saying, okay, we are going to have the same concept for resilience. Structures will be resilient, not only green, but resilient. And we will have the same category, platinum resilient structures, gold resilient structures. So when we are talking about resilient based design, after you do the resilience based design, you certify the building as resilient, on just like you certify the building as green. So green building and resilient building, 2 matching concepts, one for environment, another for resilience. Resilience means safety and everything, economy and everything. Big picture, big picture. So structural engineers are going there, top. So this is our top level now for structural engineer. Structural engineering, the highest level of our achievement or highest level of our thinking is here. This organization, I went to the last meeting, and when you hear talking to, listen to the people over there, you realize that how things are changing, right? And we need to move there at some time, right? So, but we have many steps to go. Today, we haven't even started code-based design. For code-based design, then we will have to go to performance-based design, which we are doing in AIT a lot. From there, we go to risk-based design, which some of the theses are based on risk-based. Then we go to resilient design. We already started some work on resilient design. So at research level, you can go to this level already. So you can choose a topic, thesis topic in your final year, to be on any one of those steps that I showed you. So resilient buildings, I don't want to go into details. So let me go back one more time and show you the steps. So this is what we are talking about. Code-based design, performance-based design, consequence-based. For this class, we will only study code-based design, at least the minimum level, tall buildings and bridges. Performance-based design we are doing in our offices, so that is more like practical work. We can have some seminars on this one. These 2, and then you can choose your thesis research topics to be on any of these 3 steps, right? So you can learn, if you want to learn those, you can choose your thesis to be any of those areas. Tools. You need to learn last 5 minutes, give me 5 minutes. So to be able to go there, you will need to learn many things. Dynamic analysis, nonlinear modeling, time history analysis, progressive collapse, stage construction, and many things you will need to learn beyond the normal design process. So computers are now very important. Last couple of slides. A swing towards artificial intelligence. As you know now, we are all thinking about artificial intelligence. What is that? What is artificial intelligence? Artificial intelligence is that we create systems which can think by themselves, like us, like human beings, right? So artificial intelligence is now coming everywhere. AI is everywhere. There's a movie called AI, you might have seen it. The robot, Will Smith. Anybody seen that? Yes? You saw that? Okay, so AI means many things. Rich pictures, analytical process, artificial neural network. We do research in many of these. So you can also choose topics. This time one of your senior is using this one to design the tall buildings without designing them based on the previous data. So he is taking the previously designed buildings and creating a new artificial neural network so it can design the new building without doing any calculations. So it's possible now to do that. If you have hundreds of buildings designed already, you can take that and go from when you get a new building, out comes the new building design. Not final, but it's good enough. So a lot of artificial intelligence can be built into our systems to do the decision making. Again, this is a good topic for research for those of you who are interested. Mobile computing. You already are working, some students, some of you already worked on this one. Mobile computing, how it can change structural engineering. So we are also working on those areas. So a lot of work is being done all around you. You are in a place where you have the opportunity to learn code-based design, performance-based design, resilience-based design, artificial intelligence. All of these things are open for you to learn in your classes as well as for your research. All right?